Welcome to the fourth talk of the morning session, day 3 of the iRods User Group Meeting 2020. This is Tony Edgin and Edwin Skidmore from CyVerse. They're going to talk about the data store that underlies everything at CyVerse. Here you go, Tony.
Hi, I'm Tony, and Edwin and I are going to tell you about the exciting features and development of the CyVerse data store. And Edwin in particular will talk after I do, but about the development of the continuous analysis platform. So the data store is one of the core components of CyVerse's cyber infrastructure. It manages persistent data for our users, and at its heart is iRods. So currently the data store holds about 190 million objects with 80,000 users. It's fairly busy, but it's got 50 concurrent user connections on average at all times. And we get about 200,000 files uploaded daily. Over the years, we've been working on improving our large file data transfer performance. As people at iRods can attest, we've bugged them greatly. Anyway, we're happy to say that our numbers have come up to satisfactory levels, and actually fairly impressive for us, like the Jetstream number. So again, what is the CyVerse data store? Well, at its core, the data store is a service for storing and retrieving data. Thanks to iRods and its ecosystem, the data store is highly adaptable, and we can and do extend it to meet the needs of individual users. In large part, the evolution is driven by these users. I've listed some individual features here, and the ones in bold will be discussed in more detail in subsequent slides. So all data objects in our main repository, our main resource, are replicated to corral attack, as Chris Jordan mentioned yesterday. And we make use of dabrods to significantly reduce the amount of time it takes to download large sets of small files. We also use rules attached to policy execution points to publish change events to an AMQP broker. And these events are used for various things like incremental indexing incremental search indexing. Sorry about that. Among other things, like we have an asynchronous file type detection process that runs. And finally, we do custom integrations for users. Like for instance, if a project has a large amount of storage, they can bring their own hardware, and we can configure it to be part of our zone. And so the storage will belong to that project. So, finally, we have integrations both for services and custom applications that rely on iRods PEPs to under the hood for ensuring the connectivity. One example of an integrated application is Sparked. It enables an ecological citizen sciences initiative. So going into more detail about optimizing access to large sets of small files. Well, genome browsers like JBrowse or the UCSC genome browser deal with thousands of small files. That they're interactive, and load files as needed. So they must be responsive and shouldn't take that long for each user request. When we're talking directly to iRods, it could be take 45 seconds for some of the more complicated user requests to get their data across. Well, the solution was we set up a WebDAV service with a file cache backing it. So following dabrods, we knew about dabrods, so we set up Apache web server with dabrods for iRods access, and we used mod file cache for file caching. And that improved performance greatly, except for a lot of cases with the UCSC genome browser in particular. It does a lot of byte range requests, and mod file cache doesn't allow for, it can only cache whole files. So it just ignores byte range requests. To work around that, if you know a certain set of files is going to be used heavily by a UCSC Junior browser, you access them all in their entirety, and that forces them into the cache, thus warming it. So then the UCSC Genome browser performance, response time greatly reduces. One other thing, we noticed that a lot of the data served is publicly, anonymously available. So by separating out an anonymous virtual host, so we have two dabrods is running, one for anonymous files and one for authenticated, that anonymous file access performance improves too, because there's no authentication overhead. And we've noticed that this can be up to 100 times faster than just using iGet to download the set of files. So project-specific storage. Say a project comes to us and wants to store 100 terabytes of data, and wants to bring 100 terabytes of their data into the data store for access for usage with all the rest of the cyber infrastructure. They also want their own security policy for the protection level for their data. They want the data located at their institutions, and they have 2 of them in different cities. So the solution is they provide their own storage, own servers, and they once they got them set up and into their infrastructure, we configure the storage we configure them with iRods and set them up to work in our zone. So in this case, we would set up a replication resource that would have 2 children, one that are both storage resources, one on each of the servers. And we'd set up policies to ensure that data uploaded to the project's place in the unified namespace were actually stored there. And that also would handle things like moves. So if data were moved out of there to another place, that likewise it would be moved off their storage servers and into the main storage server, and vice versa. One bit of caution here, not caution. The small bit of security we can add to it is to set them up with their own iRods Clover or service accounts, so that when the iRods resource servers, if there is an issue that happens, we can quickly just change the password of their Clover user, and then access is cut off without affecting the rest of the system. So let's talk about our future plans. Now, this is a reference to the 1939 New York's World Fair, which was called World of Tomorrow. So our utopia is having a scientific research process with no technical impediments. The research is performed and results are shared without any consideration of the facilitating technologies. In other words, not even an easy button is needed. We have no clue how to achieve this, but we do know that certain steps need to be taken along the way, and I've listed some of these steps. So we need to increase interoperability, and that's easier to realize now because people have larger repositories. They have their own Ceph clusters, AWS computes available. People have private compute clusters with custom applications and so on. And also, typically you have admin to admin communication for setting things up. Well, that's a time sink. So if you could change it so that it's user to user communication, things would go a lot more, maybe not more smoothly, but at least move along more quickly. Also, reducing accidental complexity for the user in particular. So accidental complexity is complexity that isn't essential to a task. It typically diverts the user from the task at hand. It causes frustration and drains their cognitive resources. And this results in a 2-factor loss of productivity. First, from spending time on the accidental complexity, and second, from the resulting mental fatigue. Now, there's a great blog post on, about this, and it's called Your App Makes Me Fat. I highly recommend it. And finally, shortening the scientific analysis feedback loop is, well, obviously, the faster the feedback loop, the shorter the feedback loop, hopefully the faster it converges. So here are some of the upcoming features. And again, the ones in bold we'll talk a little bit in more detail. Now we're going to bring in, for certain projects who want to share their NetCDF data sets or public NetCDF data sets, we're going to bring in, set up a thread server that will be co-hosted on top of a dedicated resource server. And that's where the thread configuration and data will reside. We're also going to bring your own, infrastructure type more features, like the example earlier was projects providing their own hardware. But anyway, provide your own storage or compute and still be able to fully use our cyber infrastructure. So, and finally, Edwin's going to talk about continuous analysis in a bit. So user-provided S3 compliant storage. This is our next, well, probably the final solution, hopefully, for users being able to provide their own storage to work with us. So with all the work that iRuds has done recently on the iRuds S3 resource plugin, makes this a reality. We can, users keep their data in the cloud and, but make it a part of our data store. And so the solution, as you got seen similarly in the last talk, is have the iRuds S3 resource plugin and use the file system scanner. So in our case, since we would be allowing for multiple projects with different places, and since we have a lot of resource servers already on premise, the cacherless detached S3 resource makes more sense, and because it can scale out to spread over multiple resource servers. As you saw in the previous talk, the file system scanner would register the data in place, and it would run on the cloud platform to avoid egress costs during the MD5 checksum generation. And of course, the project would own the cloud access credentials and could cut us off at any time, but importantly, they are responsible for accruing the costs, accrued costs of keeping the data in the cloud. Okay, so next up is Edwin's going to tell us about the CyVerse continuous analysis. So are you ready to take it away, Edwin?
I sure am. Go ahead and stop sharing, please.
Where is it? Oh.
Cool. I'm going to share my screen because if I have time, I'll try to do a demo. So let me present. Cool. So the last topic I'll tell you about is something that we're currently in development for called the CyVerse Continuous Analysis Platform. But before I get into kind of the nuts and bolts of what continuous analysis really is I want to mention a couple technologies that are key for this infrastructure. So if you're familiar with contemporary software development technologies, you undoubtedly have heard of continuous integration, continuous deployment, maybe even DevOps. The general idea is that the software development lifecycle involves frequent deployments. It's repeatable, it fails fast, meaning like if someone commits a code change, then it's automatically tested, and if that fails, then you get alerts and metrics where it failed. Everything is, of course, automated, and the entire system is event-driven. Largely focused on code events. Another piece of that technology is container orchestration. And so if you've heard of containers and the software that's used to orchestrate those containers, you've probably heard of Kubernetes. And in this graph, this represents the learning curve of Kubernetes, which is probably not too far from the truth because you could just learning it is not only steep, but can lead to a lot of pitfalls. So continuous analysis, the continuous analysis platform is really built on these technologies and trying to bring about the benefits of it while kind of hiding, making it simpler and hiding away the difficult details. But why continuous analysis? Well, in 2016, the Green Lab paper from University of Pennsylvania published an article about using modern software development tools and applying it within a scientific computing setting. So certainly it wasn't earth-shattering for software developers, but it really was a good article in illustrating how modern software development tools could be applied in a scientific setting. And the time is right for this sort of technology. So data is becoming larger and users want to be able to be aware of when data changes, but also to do things automatically, do additional compute on their data when that happens, whether it's a subset of data or maybe it's their entire data set. We also are getting more sensor type of data that's streaming into our system, and users obviously want to take action when new sensor data comes in, or even if you're talking about machine learning models or machine learning and new training data, for example, comes in and they want to recompute their machine learning algorithm. So clearly the need is there. In addition, there's actually this sea of change, if you will, where researchers and scientists are seeing containers as the de facto unit of reproducible compute. And Kubernetes is like becoming the de facto standard for orchestrating those containers. So combine that with CI/CD technologies. Obviously, there's a lot of benefits. This whole event-based driven type of model combined with reproducible compute is certainly something that as a research and scientific community, they want to leverage. But for mere mortals and scientists, it's often a challenge just to learn how to use it. Well, continuous analysis hopes to reduce that barrier. So we're not starting from scratch at CyVerse. Obviously, we have 10 years and 70,000 users that are under our belts that we've learned from, that we've helped with their scientific workflows. And recently, within the last few years, teaching them how to do containerized workflows. We also have experience in the VM cloud space with CyVerse Atmosphere, basically making it really super simple for users to use. Hold on, I don't have my chat window up for some reason. Sorry, chat. Okay, so I'm gonna have to rush a little here. So we have a lot of lessons learned. I'm gonna skip through this a little. We have example user stories. Again, the key part here is event-driven. Also, the other aspect is that we want to, users only want to be charged for what they use. And so a lot of Kubernetes and serverless technologies are out there. In particular, we bundle these in and support things like scale to zero, which is when resources aren't being used, and it will reduce the resources. We integrate with Kubernetes native workflows like Argo, or we can integrate with other types of workflows that are Kubernetes compatible. And so some high-level features, I'm going to just highlight a few. Continuous analysis is multi-cloud, so users, if they have access to another Kubernetes cloud, they can make that available within our system, and it'll push the workloads there. I talked about the auto scaling and scale to zero. It isn't, the continuous analysis is inherently event-driven. We have our own custom resource definitions, and we integrate with other custom resource definition workflows. Get is our persistence layer, meaning workflows, when they're created, are pushed automatically to get. We also use federated identity. with Keycloak, and above all, we're aligned with CyVerse ecosystems of features. So meaning we have an API, we support sharing, we also support restrictions if you want to make that only available to certain users, and we interop with all our services, our other services. Obviously, I won't get into the architecture diagram, but just to say that Destory is a key, and iRods is a key part of that. So I am just going to jump right into the demo. It shouldn't take that long. So I'm just going to talk you through this, but the current state is we're in heavy development. So what I'm going to show you is just what we're at right now. We have a CRD, we have a command line. I'm going to show you the command line. And so this is in a Git repo. This is a workflow definition. And we're showing the command line. Right now, we have some simple primitives to build a workflow, to create a workflow, to build it, to delete it, to get it, to run it. And notice we can also, there's primitives for getting clusters that the user has access to. So these clusters could be out in the commercial cloud. They can also be out in an IoT device. It's quite common today, and we have users that are interested in running micro Kubernetes, whether it's Minikube or maybe even Kind. And so a continuous analysis will push jobs out to those. So in this case, he's Calvin, we're looking at Calvin McLean's screen, who's one of the developers. He's creating a workflow, or he's defining a workflow. He just received it and got the JSON from our API. And let's see. Okay, so now he's getting information about a cluster that he has access to, and he's going to use this information to build his build the workflow. So part of building, in addition to just pushing out the workflow and testing it, but it will also build the containers if they're not already images in a registry. So he's already associated his Docker registry credentials, and it'll push it out to Docker and build it. The system will wait for it to be ready, and then when it is, it'll actually create the provision and the resources on that Kubernetes cluster. So he's building it now. He's going to run it. So, and now he's going to grab the ID from the command line of that particular deployment, and he's just showing that it's there on the Kubernetes cluster and all the resources. But one of the things is that there's to note is that every workflow in continuous analysis will have a unique URL. And this is a output. So what's not clear, what I wanted to explain was that the workflow was in Get. It's using calsay as 2 steps in the workflow. This is a command line utility, and the continuous analysis basically creates an endpoint where you can retrieve the output of the analysis. Now you can imagine these could be chained, could be sent to another workflow within the system, or maybe outside of the system. Anyway, so that's it for the demo. What I didn't get to show you was obviously the integration with data events, as in like when something changes in iRods, how that pushes or activates a workflow. That is in heavy development. The current status of this is that we have a REST API, we have a command line interface. Obviously, these aren't easy to use. The goal is ultimately is that we'll have an easy to use UI so that a user, all they have to do is provide credentials. They can click and define things. They don't have to know YAML. They don't even have to know how to use Get. And they can construct these things. It'll be available close to the end of 2020. And that's it. Special thanks to Mariah, who's our graphics designer that helped with some of the graphics on our slides. Oops, questions?
Good, thank you. And we can also potentially have a lightning talk if you want to do a demo later this afternoon, if that's interesting. to you. I think lots of people will be interested to see how these things work. Josh Moore at OME asks, what would be required for someone to deploy continuous analysis themselves? Or do they need a whole bunch of infrastructure? How does this work?
No. So we already have Ansible. It'll deploy it in a development environment using Kind or Minikube. That's already available. Obviously, there are certain requirements if you want it to push out jobs to Kubernetes. So you do have to have some Kubernetes cluster, whether it's a small deployment with Kind and Minikube or a larger one. The goal is ultimately, though, we'll integrate with a commercial cloud, so you can just provide the credentials to the commercial cloud. We'll even provision the Kubernetes cluster. That is a long time, kind of a long-term goal. It's not here today.
Right. John Constable at Sanger, he says, how many of you are there and how long did it take to make all of this? It's quite a mature and complicated deployment. He says he will definitely not be showing these slides to his scientist or they will demand it immediately.
Well, we only have, two people that are currently full-time on the project. I'm helping out on the system side of things, and then I have a couple other folks on the system side of things.
And this has taken a year or 2 or 3 to build? 6? How long has this taken?
Well, I mean, some of us have been working part-time on it, split across different projects, but I would say full-time it's been about 9 months. A lot of it was learning kind of the right pieces. Also, there was a lot of backtracking because as some of you already know, Kubernetes, the Kubernetes ecosystem is moving super fast. We actually adopted one technology only to realize it's not going anywhere. So we had to rewire everything to use, we're actually using a technology from Azure called Keta. It's a serverless technology, and so we had to rewire a lot of to use that because it just had more functionality. It was growing at a rate that we felt comfortable with, and so on and so on. So, but there's a lot of reasons why it took a little longer than where we should be.
That's right. And you said a lot of this code is already public. Maybe you can share a link also that's clickable in the channels. I think that's about it. We've got we're right on time. So thank you both. Thank you, Tony. Thank you, Edwin.
You're welcome.
And,
Thank you.
Talk to you again soon. Thanks.